Hello. All right, we're picking up with bonding in molecules. We're going to look at molecular orbital theory and molecular diagrams now. So the electrons in molecules have a spatial distributions, which are described by the one electron wave functions, which are the molecular orbitals. So in our approach, we're going to use the Greek letter psi to represent the molecular orbitals and chi, which represents the atomic orbitals. And the fundamental difference between the molecular orbitals, they are spatially delocalized over the size of the molecule. Depending on what that molecular orbital is, it can be greatly delocalized over the entire length of a long molecule if we're looking at a conjugated system. We're going to start with much smaller molecules. We're going to start by looking at diatomic molecules and build up this sense of what molecular orbitals are. So we're also going to use the same wave function principles that we used before. The probability of finding an electron at any point r in space is just given by the square of the wave function. So psi squared integrated over all space. Or rather, within an infinitesimal d tau. Just to bear in mind that when we use this equation, the r is the three-dimensional coordinate. So it's either x, y, or z, r, theta, phi, or if we're using the polar coordinates, the cylindrical coordinates rather, that we saw earlier, it would be z, r, and phi, that azimuthal angle. Okay, moving on. All right, we're going to talk about linear combinations of atomic orbitals. That's LCAOs. It's an approximation that we'll use to build up our molecular orbitals, just in the same way that we built up our atomic orbitals. So the way we're going to do that is we're going to define the psi for a specific molecular orbital is going to be the sum of some combination of atomic orbitals. So that is the that chi sub I. So we'll have some kind of a contribution from a number of orbitals. Depending on what the symmetry of the molecule is, what atoms are bonding in the molecule, we'll see that the contributions to the molecular orbital by the atomic orbitals will vary. Okay, and then just like in hybridizing orbitals, the number of atomic orbitals we're going to take and put together to build our molecular orbitals, we're going to get just as many molecular orbitals at the end that we have of atomic orbitals that go in to make them up. Another thing that's going to happen in this example is when we have dissimilar orbitals, and we'll look at this with the heteronuclear diatomic molecules, what's going to happen with heteronuclear diatomic molecules is we'll have a break in symmetry. We'll have one atomic orbital be closer in energy to one of the molecular orbitals. And because it's closer to it, that molecular orbital will more resemble that atomic orbital. So that is to say, those coefficients in the equation at the top of the page there, that coefficient c sub I for each chi sub I, when a molecular orbital is closer to a certain atomic orbital, it will have more of a contribution from that atomic orbital than from the other ones. So we'll see that moving forward. Okay. All right, molecular orbitals are formed as linear combinations. Here we're going to look at the hydrogen molecule. So either ionic hydrogen, which remember we saw as our simple example, it's just 2 protons and 1 electron, or we could look at diatomic hydrogen. And again, we're doing something similar to what we did with two electrons in a system in an atom, we're going to have the molecular orbital be an approximation of the orbital with just one electron in it. That is, we're not going to be able to account for electron-electron repulsion by solving this completely, so we'll make approximations as we move forward. Okay, so what's going on? And we saw this with our bonding models as well, that if we think about this diatomic hydrogen, the molecular orbitals are formed as linear combinations of the hydrogen's 1s orbitals. So on the left side of the screen, we have hydrogen number A, hydrogen letter A, with its wave function chi sub A, which is just its 1s orbital. And on the right side, we have hydrogen B with chi sub B. So that's two atomic orbitals. We're going to bring them together, and we're going to have to make two molecular orbitals. Just like when we hybridized orbitals in the last lecture, we saw that if we're going to take an s and a p orbital on a single atom and allow them to mix and split into sp hybrids, we need to get two sp hybrids because we've taken a single s and a single p. That's two atomic orbitals. We need to get two hybrid orbitals. So here we're not doing hybrid orbitals. Here we're just doing bonding orbitals. Well, bonding. So if I take the hydrogen 1s and overlap it with another hydrogen 1s and have a bond, what's the other orbital, right? I need to get two molecular orbitals at the end of the day. And so very similar to the way we did hybridization, we're going to have to do this combination where we have two orbitals resulting. So here we're going to have psi plus, which is going to be the positive overlap or the in phase or the constructive interference overlap between the hydrogen 1s on the hydrogen A and the hydrogen 1s on the hydrogen B. The other orbital is going to be this weird idea where it's the destructive interference. It's the out of phase, and it's what we call anti-bonding. This is a worse configuration of the orbitals. Worse in the sense that it's going to be higher in energy than if we just didn't bond the two atoms together. Okay, so let's see what that means when we look at this in terms of taking our two 1s orbitals and seeing how they interact. Now, they're going to start off at some distance r apart. So we're considering in this case the properties of the bonding orbital. Let's leave aside that anti-bonding orbital for a second because it's a little confusing. The bonding orbital we're going to have for a large r, and this is just like how we saw with our potential energy surfaces, especially the potential energy surface for hydrogen, right? When r is large and the two orbitals are not really interacting with each other, they're going to behave as two independent hydrogen 1s atomic orbitals. But when r gets smaller and our two atoms come into close interaction, there's going to be a significant overlap between those atomic orbitals. So what does that mean? Well, it means we're going to have constructive interference between the two atomic orbitals. So chi sub A and chi sub B will increase the electron density between the two nuclei. That region right in between the two nuclear centers is going to have a lot more wave function density, and therefore psi squared is going to go up. So the probability of finding the electron in a region between the two nuclei is going to be higher because that's the constructive overlap between the amplitudes of those wave functions. So that's what the bonding orbital means, that there is this sort of I don't know, sweet spot in between the two nuclei where the electron density is increased. So that's what bonding is. And we build a new wave function, which is the bonding wave function. It's that psi plus. Okay. So that means that the energy of that psi plus in that region between the two nuclei, the energy is actually lower than the individual contributions of the unbonded atomic orbitals. That is, when we allow these two orbitals to come together, the overall energy decreases. So when we allow the energy to go down into the well, that is bonding. That's more stable. We're going to have to put energy into that if we want to break them apart, right? So that's a bonding orbital. And we call it covalent because the valence electrons are being shared between the two orbitals. They are a valence, or between the two atoms. They are a valence electron as far as the hydrogen atom A is concerned, and they are a valence electron as far as the hydrogen atom B is concerned. So it's covalent. And we've talked about the type of bonding. This is a sigma bond, and it's a sigma bond because it has cylindrical symmetry about the internuclear axis. That is, we've taken two spheres and we've allowed them to come together and they're overlapping in a head-on way. So that on the bottom left-hand side of the slide, we see the side view, right? That positive, that's the positive sign of the wave function. It's now overlapping completely, and we have this oval type wave function because it's all bonding, all positive amplitude of the wave function. And if we look, so that's the side view that is perpendicular to the bond axis. And then if we rotate that around and look along the bond axis, excuse my voice, if we look along the bond axis, we can see that the cross section, it's just cylindrical symmetry, right? It's just two spheres that have overlapped along the bond axis, and that gives us our sigma bond. Okay, so now we're going to do the same treatment. We're starting with our two 1s orbitals at some distance r, but now we're going to look at the properties of sigma minus. This is the antibonding orbital. So antibonding is kind of a strange thing to happen. For large r, we're in the same boat that we were with the bonding orbital. There's pretty much no interaction between the two orbitals, so they are independent atomic orbitals. But allow them to come together again for small r, and now they're overlapping again. Again, a significant overlap, but this time, instead of them both having a positive amplitude, one of them has a negative amplitude, and it is destructive interference. And in that region, right in between the two nuclei, we have a node, right? We have the two wave functions essentially annihilating each other right in the middle of that wave function. So what does that mean? That means that there is no probability of finding the electron in exactly the middle of that wave function. This is a worse arrangement for the electrons to be in as far as energetics is concerned. This is why it is called the anti-bonding orbital. So in an anti-bonding orbital, the energy of the psi minus is greater than the energy of the two individual atomic orbitals had we not allowed them to bond. So that is the anti-bonding molecular orbital. It still has its cylindrical symmetry. If we were to look along that bond axis like we did before, we would see that it still has that, we have the circles overlapping along a straight line. So it's still going to have sigma bonding symmetry, but now it's got a nodal plane right down the middle, right in between the two nuclei. That is a plane where the probability goes to zero. Just like we have that plane in a p orbital, an atomic orbital, but here we have it in a molecular orbital. So this molecular orbital looks a little bit like a p orbital, but it's not, because the bond axis tells us that it's a sigma orbital. And because it's anti-bonding, we're going to include that asterisk after it. So we call it a sigma star molecular orbital. The star means that it is anti-bonding, that it is higher in energy than if it were just a regular non-bonding orbital. Okay. So we can think about what the normalization constants are in this case. We're looking at the normalization constants for our hydrogen 1s overlap. And we have our two orbitals that we want to consider here. We have the bonding, the sigma plus, and the anti-bonding, the sigma minus orbital. And they'll each have their own normalization constant. They won't be the same as each other. So what's that normalization constant going to be? Well, we know how to calculate a normalization constant. We're going to do psi star psi and take the integral over all space. And because for in this case, our psi's are made up of 1s orbitals, the 1s orbital on nucleus A and the 1s orbital on nucleus B. So they're on the two different nuclei, which is going to matter, right? We're going to get up to this in a second. They're not on the same atom. They're on two different atoms. But those don't have imaginary parts to them because they're 1s orbitals. So we can just write psi squared d tau. And you can see that we have the psi plus or minus. Plus or minus because we can either do the bonding orbital or we can do the anti-bonding orbital. We're not doing one of each, right? We're just doing either the psi plus case or the psi minus case. So in this slide, for this example, what we will do is we'll take into consideration the psi plus case and we'll normalize it. So we're going to set psi plus squared d tau equal to 0. So that means we're going to have the quantity n plus, which is the normalization constant for the psi plus wave function, times the quantity chi A plus chi B. Those are the two individual atomic orbital wave functions. Those are our 1s wave functions. That whole thing squared and integrate the whole thing over d tau. So if we set that up, we can see that we pull the constant outside of the integral, and the integral breaks down after we take the square, right? We're going to get three terms from that. We're going to get the chi sub A squared term. We're going to get the chi sub B squared term. And then we're going to get two terms of chi sub A times chi sub B and integrate that, integrate each of those individual terms. Okay? Well, remember what we did for a whole half a semester where we normalized our individual atomic wave functions so that we know that chi sub A squared d tau is going to equal 1 and chi sub B squared integrated over d tau over all space is going to equal 1. We set those integrals up in the beginning so that when we got to this point, we wouldn't have a really complicated math problem to solve. So the first two terms in that set of integrals are 1. Okay, so what about that third term, that integral of chi A times chi B over all space? Now, remember we had orthonormal wave functions. But you can see in this slide where after the part it says, and we will define a new term, the overlap integral or the overlap density. The overlap integral S sub AB, why doesn't that just equal 0, right? I thought these were orthonormal functions. Shouldn't it just go to 0? And the answer to that is no. Orthonormal only works if you're looking at wave functions that are centered on a single atom. Here we have two wave functions on two different atoms that are overlapping with each other. They're going to overlap with each other in some way, right? This is where the bonding is coming from. So that integral has to do with the distance between the nuclei. It has to do with what the wave functions are. It has to do with what direction they are. But in general, that's going to have some value, and we'll have to learn how to evaluate that in different situations. So that value here, though, we'll just define as S sub AB. So now we can go back and find what that wave function, what that normalization constant is for our bonding orbital with the constructive overlap between our two 1s orbitals. And it's going to be, once we substitute everything in and solve for n, we're going to get that it's the square root of 1 over 2 times 1 plus S sub AB. That is the normalization constant that's the normalization constant, but only for the positive overlap, for the bonding orbital. All right, let's go on to the next slide and see what happens with antibonding. Okay, so what we can see is we got on the last slide for the bonding orbital psi plus, we got that 1 over 2 times the quantity 1 plus S sub AB square rooted. And we can go through, you can prove it yourself by going through this math, pretty simple math on the last slide, but do it for the psi minus wave function, and you'll see that you get a very similar result, except that the sign inside the radical in the denominator on the S sub AB has flipped. So that is to say it is going to be minus S sub AB rather than plus S sub AB. S sub AB, that is this interlap integral, is going to have some value between 0 and 1, which means that when we go through this, we'll see that the normalization constant for the antibonding orbital is always going to be greater than the normalization constant for the bonding orbital. And we can do similar math and use similar arguments to show that when we look at the energies of these two wave functions, we're always going to have a higher increase in anti-bonding energy than we have for a decrease in bonding energy. In other words, the benefit that we get from forming a bond in a given molecule does not outweigh, in fact, is outweighed by the penalty we would pay for having an anti-bonding orbital. So it's more expensive to put electrons into anti-bonding orbitals than it is to put them into bonding orbitals. I'll explain that a little bit more in the next slides when we're looking at the molecular orbital diagrams, because they're a lot easier to picture than explaining it in words. The other thing to note here is if we were to drop out that overlap integral, or rather, let's say at r equals infinity, where there's no overlap between the two wave functions, well, we would imagine that overlap integral goes to 0. So what happens when the overlap integral goes to 0? Well, we see that we just have the 1 over the square root of 2 term left. Well, 1 over the square root of 2, that's how we do a normalization for two wave functions. We're putting two wave functions together, and they're not weighted, and they're equally weighted, then that's the normalization constant that we use. So we can see that we get to our standard way of doing things if the overlap integral goes to 0. Okay, let's move on. All right, molecular orbital diagrams. So you may have seen these in freshman chemistry. We're coming back to them. We're going to go into a little bit more detail on these. So what's going on in a molecular orbital diagram? It's a much better way, or it gives us a lot more information than doing our valence bond theory that we did, where we just look at overlaps. Because when we just look at how two wave functions overlap with each other, what we're leaving out is that two wave functions that overlap form one bond, and they form another bond. But where is that other bond? Well, now we can see both of them. We can see both of these orbitals, right? We can't just take this orbital and overlap them to get a bonding orbital. There needs to be a second orbital somewhere, and that second orbital is the anti-bonding orbital. And you can see here that, so we're starting with some examples to go through and explain this. We're going to start with the example of diatomic hydrogen ion, cation. So 2 protons, 1 electron. So you can see in this molecular orbital diagram, we have the atomic orbital wave functions are on the outsides of this diagram. So on the left side, we have the hydrogen 1s electron for atom A, and call it chi-A. And on the right side of the slide, we have the hydrogen 1s electron for atom B, call that chi sub B. In the ground state configuration here, the bonding orbital has 1 electron in it. So you can see the ground state is in green, and it's shown in that diagram, the potential energy surface diagram in the upper right-hand corner. You can see how the bonding orbital goes through its minimum and then goes up to infinity as the two nuclei get very close together and start to repel each other. So we saw that in the last lecture on potential energy surfaces. So here, that's the bonding part. What we didn't see when we looked at the bonding part in valence bond theory was the anti-bonding part. That is, if that electron were in an excited state, if it were promoted to the next lowest energy level, which is that psi minus energy level, it would be on this dissociative curve, on this exponential decay of sorts, where as the two nuclei get together, the parking space for that electron, the energetics of it just get worse and worse as the two nuclei get closer together. Remember, as they get closer together, the destructive interference of the electron clouds is getting worse and worse. So it doesn't have to wait for the two nuclei to get close to each other to start repelling each other. It's going to, as soon as these two electron clouds start, or as soon as these two wave functions start to overlap, they start to destructively interfere with each other, right? That is what anti-bonding is all about. It's the destructive interference of the two wave functions. So that is that upper state, and then the lower state is the bonding state. So that's what the energetics for our single electron in diatomic hydrogen looks like. So what happens if we go on and look at regular diatomic hydrogen? This has 2 electrons in it. Now here we're only going to consider the ground state, the bonding orbital. Right? In the ground state, what we have are 2 electrons in the psi plus bonding orbital. So that is the regular bound state of diatomic hydrogen that we find in nature. It doesn't want to, and it does not, not in the ground state, doesn't put its electrons into that upper state. That is to say, it's a virtual orbital. The orbital, the antibonding orbital in hydrogen exists, but it isn't being used. So that is to say, when these two wave functions come together, it creates a bonding orbital, which we see in green, and an anti-bonding orbital, which we see in red, but it doesn't use the anti-bonding orbital. So it's there because it has to be there. If we have one orbital over there, if we've taken two orbitals, two atomic orbitals, and we've made molecular orbitals out of them, we have to make two molecular orbitals. So even though that second molecular orbital exists, it's not being used in diatomic hydrogen. On the inset here, we can see in that figure the difference in the energetics between diatomic hydrogen with 2 electrons and the cationic diatomic hydrogen, which just has 1 electron. So two things to notice about what happens with that potential energy curve. That first number, R sub E, that's the equilibrium bond length. When we put that second electron into the bonding orbital, what happens? Well, we've increased the bond strength, and because we've increased the bond strength, that bond distance has decreased. That is, the well is deeper, and the bottom of the well, of that green part of the well, is closer. It's about 25%, 30% closer. So the two nuclei are going to want to be pulled closer together if we have that second electron in diatomic hydrogen, because it's a stronger bond. Stronger bond also means that it's got a deeper energy well. So that D sub E, that's the dissociation energy of this bond. You can see it goes from 255 kilojoules per mole to 430. Now, it's not quite twice, right? If the electrons didn't interact with each other, we would expect it to go from 255 to 510. It should just double the depth, right? Because if we have two electrons each in that well, each increasing or each decreasing in energy by the same amount, we would expect it to double. But it doesn't quite double because the second electron is going to see that first electron, just like it happens in the two electron system for helium. In atoms, right, that second electron knows that the first one is there. It's feeling this repulsive force, so we don't get this 100% doubling of the bond strength. But we get a lot more bonding when we put in a second bonding electron. Okay, hey, speaking of helium, why not diatomic helium? You never hear much about diatomic helium anymore. I wonder whatever happened to it. Well, you don't hear about diatomic helium because diatomic helium is not a thing. Why is it? Well, it's not a thing in the ground state. It does exist under certain conditions, but you have to move some electrons around. And here's why. In the ground state configuration, we have two electrons in that bonding orbital, just like we had the two bonding electrons in hydrogen. It's the exact same orbital. But we also have two more electrons. And because we've allowed these two atoms to come together to bond, they also have to come together to antibond. We can't have the bonding come together. Once those two atoms are r distance apart, the two orbitals, the bonding orbitals have gone down and the antibonding orbitals have gone up. It's fine. Those antibonding orbitals can go up as high as they want as long as we don't need to use them. But with diatomic helium, we have to account for 4 electrons, 2 electrons from the first helium and 2 electrons from the second helium. So those third and fourth electrons in the diatomic, in what would be the diatomic molecule, have to go somewhere. Well, the only parking space we have left for them, or the lowest energy parking space we have for them right now, is in the antibonding orbital. So we're going to call that the 2 sigma star orbital, whereas we call the first one 1 sigma, the second sigma orbital, so we'll just give it the number 2. And we're going to put a star on it to indicate that it is anti-bonding. Okay, but remember we said, and you can see it in this graph, that the anti-bonding orbitals are slightly higher in energy than the bonding orbitals are lower in energy. So that is, there is more of an energy penalty here to form diatomic helium than there is a benefit. As a result, we don't have diatomic helium. Helium would prefer to remain, energetically, helium prefers to remain as a monatomic substance rather than form a diatomic molecule. So when we think about what helium is held together by, like in liquid helium, those are just the dispersion forces that hold them together. And that's a discussion of intermolecular forces that we saw in Physical Chemistry 1. It's not a bonding energy. We can note that at the bottom of the page, you talk about the ionic state, helium plus. What happens if we get rid of an electron? Well, if we get rid of an electron, then we will have two bonding electrons in that lower energy state and only one antibonding. In that case, we can have diatomic helium, but it's only diatomic helium cation. There's also a form of excited state, diatomic helium, and we talk about excimer lasers. We can talk about that, but that's getting a little ahead of ourselves here. Okay,